So it's really an honor and a pleasure to be here for this celebration. I think I met Frank mathematically. I think I was second-year student at the École Normale, maybe around 96. I mean, during a reading group to discuss the work of Bourgain that was mentioned in the previous talk. I think at that time I was doing fluids. I always do fluids, but for me it was the occasion to learn something else. And they kept notes of that reading group. It was always very helpful to go through those things. I think it was with Patrick Gérard and also Jean-Marc. So I really learned a lot from that reading group. Okay, so my talk today will be slightly more about fluids, so reversing in stationary Prandtl. Since I see that there are many young people, I always like to start by mentioning some of what I think are interesting problems now in the mathematical analysis of fluid dynamic. I think about problems about stability of simple flows. So many questions that may seem trivial are really hard, like in trying to understand stability of even of very simple flows, long-time dynamic. There are many also problems about transition between laminar and turbulent flows, inviscid limit. So the talk of today is related to inviscid limit, describing singularity, boundary layer separation, and then applications of these ideas to other problems. I mean, now I've been more interested in questions like crowd or traffic flow and so on. So this is, for instance, like a picture if you want to understand stability of a vortex. So I'll go fast maybe through some of these things. One fascinating question is also, for instance, the red spot on Jupiter, understanding why this structure is there. So this is the idea of transition between a laminar flow and a turbulent. So usually there is a region where we have this transition, and we can try to describe precisely how the transition takes place. I mean, this is not a very clear thing, but it shows like how we can go from areas where we are laminar to areas where we are turbulent. Okay, today's talk is about boundary layer separation. So if you think about this as a wing of an airplane and you have a flow, you see that the flow here stays attached. So whereas here the flow, we say that it separates. So the talk today is more about this region. After it separates, so this is here the point of separation. After it separates, what can we say about that flow? Can we find a good notion of solving and so on? Okay, so if I try to put a physical setup, we want to think about the problem in half plane, and you can start from Navier-Stokes with small viscosity, and then you expect that when the viscosity goes to 0, your solution will be approached by Euler. Okay, the only problem with this naive way of thinking is that for Navier-Stokes we impose 0 boundary condition here, whereas for Euler we can only impose non-penetration, that the normal component is 0. So typically this will be like the Navier-Stokes, and this will be Euler. So Prandtl, in 1904, this was at the International Congress of Mathematics at Heidelberg. So he proposed this idea that maybe now seems simple from ODE point of view, that you introduce a rescaled variable, but at that time I think it was a revolutionary kind of idea that we expect viscous effect to be concentrated in a very tiny region close to the boundary. So, so now if I think about mathematical question related to Prandtl that I'm going to write, I will put them in two kind of categories. So there will be, I will start with the second one. Like there is many questions about Prandtl itself. So it can be local existence, singularity. These are questions about Prandtl. And then after you solve this question about Prandtl, you have to understand what they mean at the Navier-Stokes level, right? Today talk will only be B. I'll mention result about A, but I mean we should keep in mind that whatever we prove at the Prandtl level, normally we want to understand the counterpart at the Navier-Stokes level. Okay, so yeah, so that's to say that I'll be talking about. Yeah, so now today I'll be even working not on the time evolution problem, but on the stationary problem. So the stationary problem means there's no time derivative. So here, if you take the Navier-Stokes and you rescale it, this is the system we get. This is the Prandtl in the half space. Now, this term ux, if u has a sign, so if u is positive, which physically means that you have a flow going in one direction, then you can think about x as a time-like variable. Y will be a space variable, and then this equation will be like a parabolic equation. Let's ignore this term. I mean, this has this is a non-local term that comes with its own difficulties, but if you forget about it, you can think about this equation as a parabolic equation as long as u has, let's say, as long as u is positive. Of course, this will be like a non-local parabolic equation, and one can ask questions about well-posedness, regularity, large x asymptotics, singularity. So all these questions can be asked at this level. Let me mention there's a term here important. Normally, this will be normally the pressure coming from the Euler flow above Prandtl. So the main reference is the work of Oleinik, who proved result when u is positive using the so-called von Miles transform. I'll talk about it at some point. Okay, now I'm going to go to few slides where I talk about results about Prandtl, first in the time evolution case, then in the stationary case. Now, in the time evolution case, usually when we talk about the Prandtl system, as I said, we'll have these two kind of questions. Question about local existence, about solving Prandtl. So usually we have two classes that are understood now, that a class where the flow is monotone. So if the flow is monotone in the time evolution case, then we can, there is also a paper of Oleinik. There is a paper of Oleinik, but nowadays we understand this better in the monotone case. Then there are another class where we can solve, which is a Gevrey regularity class. One can also mix these things, and there are also results about ill-posedness in Sobolev, meaning that like Gevrey or analytic regularity is necessary for if we want something general without monotonicity. So this is has nothing to do with Navier-Stokes, these results. Then yeah, these are also results, extensions, also about Prandtl, smoothing effect. So there are many, all these results are still about Prandtl. And recently with, also with Charcolo, with Tej, Goul, and Slim Brahim, we are trying to understand the singularity for the time evolution problem. So this is, again, about Prandtl. Then we have, as I said, we have also many results about Navier-Stokes, trying to prove or disprove in different kind of situation whether Navier-Stokes is well approximated by Prandtl. So very nice result of Grenier, Yango, and Nguyen, like characterizing the possible instability in the limit. I mean, in a sense, now the kind of like the general conclusion is that this so-called TS instability is really the obstacle to proving that Navier-Stokes converges to Prandtl. Okay. So now I'm back to the steady case. I'm forgetting completely about the, I'm going to forget completely about the unsteady case, just concentrate on the steady case. So one term that showed up in the right-hand side of the Prandtl is this pressure term. And it turns out that depending on the sign, if it has the good sign, it's pushing, in a sense, the flow to stay monotone. So if you stay with the it's pushing the flow to stay positive. So let's say if you start with a positive, it's not difficult to see. So you see you have u, ux. So if this term here is positive, if this has the good sign, it's pushing you to stay positive. I mean, you have to prove it. It's not completely trivial, but that's was already understood even by Olenek. However, if it has the wrong sign, now that's what in the physics literature will be called adverse pressure gradient, then one can expect what we call separation. That at some place in the flow, in your flow, you will try to become negative. And then one can actually prove that it can only happen at the boundary. Now also there is Blasius, who was a student of Prandtl, proposed a self-similar solution to Prandtl. You see here the parabolic scaling. There's a parabolic scaling. So this is an exact self-similar solution of Prandtl, with this equals 0. Okay, and turns out disagree really with experiment, and one can prove. I mean, it's not completely trivial, but one can prove that solutions of Prandtl relax when x go to infinity to this Blasius profile, right? So it's like thinking about the Gaussian for the heat equation. So those are kind of result on Prandtl, but then, as I said, one can try to prove similar things at the Navier-Stokes level. So here, for instance, this is a result where we try to prove such kind of things on the Navier-Stokes level. Now, what is the other thing? So what happens if we have separation? So this is normally the point like that we see all in many pictures where we see the boundary layer separation. So this is the point where du over dy become 0, right, at the boundary, right? And then it starts, and then the flow starts going back, right? So before here, so this is y. Think about this as y, and this is u, right? So y is like this, but y is like this. So here, du over dy is positive, but here when you get to this point, du over dy, when you get here, du over dy is 0, then it starts becoming negative. It goes down, right? And Prandtl already realized that this kind of situation should happen. So this is like, for instance, in a picture, this is what happened here at this point, right? And there the flow reverse. So so in the physics literature, this was studied by Goldstein, 1948. So he made formal expansion to try to understand how this happens. Also, Landau has some nice work trying to also characterize how that happens. In a paper with Anne Lore, we proved rigorously, like studying the profile. So it's really a work, I should say, was very, very much influenced by your work with Pierre. So like all the blow-up technique, and so that was a paper with Anne Lore. So today I'm not talking about this. I'm not talking about the separation itself, but I'm going to talk about what happens after, right? So Goldstein, in his work, first he studied the separation, but then he tried to understand what happened just after separation, and he did a lot of formal calculations, not very successful, like SIM doesn't converge, like, I mean, I spent a lot of time trying to understand, but I gave up. I mean, it doesn't seem to converge, and then there are a lot of people in the physics literature who think that the expansion doesn't work afterwards. Like, after the point of separation, the expansion doesn't work. But what it really means, people really try to understand what happens really here at this point. Just after separation, they wanted to write down some sort of power series expansion. I think then people realized that actually, physically at this point, Prandtl is not the good model, right? So I'll talk about that. I mean, there is whole work in the physics literature about trying to understand what happens at that point. Today, I'm not trying to say anything about this point, but I'm going to try to say something after, right? And after, we expect Prandtl to be valid again, at least in some region. Then what is expected is that here the flow becomes turbulent, right? But after separation, it's especially like if I go to Navier-Stokes, after separation, if we stay with a small Reynolds number, meaning like large viscosity, we can still see a reversed flow even after the point of separation, which is stable. Okay, so the goal here is to study the reverse flow regime. The reverse flow regime. Okay, so basically, part of the problem is to ask the right question here, like, because you have to find what is the right way of asking the question, because clearly now U is not positive everywhere. So the idea of thinking about this as an evolution problem in X breaks down, right? However, I mean, we expect U to stay positive here above this curve and be negative here, right? So it still can make sense to think about here some forward parabolic and here some backward parabolic equation. Okay. There is also this term that will put some difficulties, but I mean this is a non-local term, but fortunately we have ways of dealing with. So there are different kind of transforms I will mention, so that work. So this will not be a major problem. Okay, so this is how one should pose the problem. Normally I should take this, put some boundary condition here, put some boundary condition here. Okay. So if I try to put this in a big picture, like these are problems which are like mixed type problems. I mean, even though it is, I mean, it's positive parabolic, negative parabolic, so it is mixed type, and we can compare it like to results like this trichotomy, Keldysh kind of equations. The work that is more related to ours is this one. So work of Bawan Digrizvar, this was very interesting kind of work that was very helpful. But our case will be more like a quasi-linear mixed type, meaning here in the linear case, usually you know exactly where is the interface between the two kinds, like the elliptic and the hyperbolic. That will be linear, but for us here, a priori, I don't know where is this curve. So this curve will be part of the problem. So that's why it is like a free boundary. So one can put it at the end as quasi-linear free boundary mixed type problem. So, so some work, I mean, recent work of Chen, Feldman, I mean, there is a parallel with what we are trying to do here. Let me also mention some work of Dalibar, Marbach, and Rax, who studied this equation, so without the non-local term. So, okay. So now you can ask me, okay, I mean, maybe what I'm trying to do is the empty set. Maybe there are no solution that can do that, right? So, like I'm starting off from where? So, hopefully the good thing is that there are actually, in the physics literature, we can read this Falconer scan self-similar profile. So these are exact solution. These are exact solution of Prandtl that exhibit this reversed flow, and they occur if you have a flow that hits an angle. So so if you look at a flow that hit an angle like this, and you try to calculate the self-similar profile here, the self-similar profile will have this reversed flow, right? And okay, this is an exact ODE. I think I guess this can be a good problem for the école normale. Like if you want to, if you're looking for problems. I mean, it's a whole paper to study this ODE proof existence. It's a paper of Stewartson who. It's a hard question. Even like proving the existence for this is not completely trivial. But okay, but the good thing is that we have solutions that have this reversed flow. So then, for me, what I'm trying now to do, I can tell you, let's take this Fs profile. It is an exact solution, but I'm going to look at it a little bit past the point where separation takes place. So here, in a region like this, where there is a reverse flow, and I'm going to prove stability, right? So what I'm going to do is I'll put some data here, I'll perturb the data here, I'll perturb the data here, and then prove stability inside, right? So, okay, so it's like you try to prove the stability of zero for many equations, right? So it's really of that flavor. I don't have to be perturbing the Fs profile. I can be perturbing also any solution. I can say, okay, assume that there is a solution here that I don't know, like any kind of solution. I can ask the same question. I can perturb. I can put the data here, and see how it behaves. Okay, so if we are thinking in terms of stability, what I would like to say is to prove is that, I mean, there will be a solution inside controlled by the data I put here and here, and that also the free boundary will move a little bit, but in a controlled way. So that will be the goal. The goal is to perturb on the left and on the right and prove the stability inside. Okay, so let's say I'm taking this Fs profile, right? So this is my solution of Prandtl. This is the free boundary. This is where UFS vanishes, right? So my UFS vanishes on that curve, that I called lambda g of x. And then I perturb my Prandtl solution. Also the V will be perturbed, and let's say my free boundary is perturbed. The way the new free boundary is defined is where my new solution vanishes, right? Right, so I end up with a coupling between two things, this vector field uv, which is the perturbation of my Fs profile, and E of x, which is the perturbation of the free boundary, right? So then I need to write an equation on this and prove good estimates and so on. So again, just to put the setup, you start with the blue line, you perturb here and here, and I try to calculate the new red, I start with the red. Okay, I start with the red lambda g. So I start with the red curve where UFS vanishes, and I want to calculate the blue line. Okay. Okay, now if I want to say the kind of statement, so there will be a discussion, I mean, I'll explain it. There will be a discussion on exactly what I'm going to impose here on the left and on the right. I'm not going to necessarily impose the velocity, but some good variable. I'll explain it. But the statement goes like this. There are two kind of results that we can prove. There are two kind of results that we can prove. The first result correspond to the case where L, the distance between these two, L is small. So if L is small, we can prove the result. And the second possibility is that we can allow L to be large, but then I have to avoid certain values related to some eigenvalues of some Schrödinger operator that arises in the analysis. Okay. I should also mention that the first result, the L small result, For that, I don't need necessarily the FS profile. I can be working with any solution that I perturb. However, the second one, where I'm allowing L to be large, I have definitely to be working with an FS profile, because at some point we use some analyticity of the profile. So you have to study some Schrödinger type of operator, and then we use the analyticity of the profile at some point. Okay. Now, as I said, the data here, we are giving it in terms of this omega g, which is some good unknown. But for now, we can think about it as the velocity. We should not worry too much about it. Okay. So the good unknown is some sort of combination of dyu and u. Okay. Usually, I don't try to spend time on this, but I'll try to explain the two kinds of transformation that come with Prandtl. So usually we think about Prandtl as so equal, let's say, 0. So as I said, the v poses a problem because it is a non-local term. So v, you have to think about it as recovering, it's an integral of ux, right? So not only it is a non-local term, it loses a derivative. So, I mean, it's not clear how you think about this as an evolution equation since the v is here, right? So ideally, you want to combine these two together. You want to combine them together and see it as the x derivative of something, right? So there are here two tricks. Either one that I will call some sort of generalization of the Krokó transform, and the other one that I will mention also is the generalization of von Miles. Both were used by Olenek in both her works on the steady and the unsteady. However, we have new ways of revisiting these things and rewriting them in the physical variables. It's much easier to understand. So, so the Krokó transform, and that will explain the variable there, is if you take a y derivative here, so I'm using uy to mean the y derivative. So you can ask me, oh, what if the y derivative hits here and here, that term cancels by the incompressibility. So now you look here, and one can cancel these two terms together. One can cancel these two terms together, but that only happens that you can do it easily if uy has if uy doesn't vanish. If uy doesn't vanish, one thing you can do is that you take this equation, you multiply it. Oh, okay, now just to simplify things, I'm linearizing this. I'm linearizing around some fixed profile. Right, that's my UFS. So let's say I'm linearizing around UFS, and then I can get rid of this v derivative by multiplying this by u bar yy divided by uy bar. Okay. So if I take the second equation minus the first one, the second equation minus the first one, this term disappears, right? And that's really what we call the good unknown and that works if u bar y, let's say, is positive. So first, this idea was used, like, I think the first paper was my paper with my student Wong, where we did the time evolution problem, the time evolution problem where we need usually this kind of conditions, right? But this is here, we have to use this close to the interface, because close to the interface, we will have this kind of condition satisfied. So this transformation is good close to the interface. Okay. I'll then mention what we do away from the interface. Okay. So that to explain really why we impose the data on these guys. So then, as I said, in both cases, either L very small or L avoiding this sort of countable values, we can prove some stability estimates. Okay? You can ask me, what about existence? Do we have existence? Right? That's another work, actually. So we have a paper to prove stability, proving existence. Proving existence. So if I impose data here and here, in full generality, we don't necessarily have existence in the right regularity space. So we need some codimension, like some compatibility conditions. We need some compatibility conditions on the data so that we can prove existence. Okay, so this is also well done in this work of Anne Lore with her collaborators. So let me not talk too much about this. So in a sense, you impose part of the data. You can impose part of the data on the left and on the right, and then there is another part which has to be decided so that you can solve in the right regularity space. So it's really like it's like compatibility in parabolic equations, but even more. Like you need some kind of global condition. Okay, let me not. Yeah. Okay. Now let me go now to the proof. Right? Let me spend some time about the proof, because one part of the proof, again, modulation. So this is something, again, we learned from Frank. How am I going to fix my boundary, my free boundary? Like, normally, I'm perturbing the problem here. So then the free boundary is an unknown. Right? So I have problem. What is my free boundary? So, I mean, in this case, I think it's easy. I mean, you can, of course, one has to think about it, but it seems easy that you say, okay, I just take the curve where the new u is vanishing, and I'm going to define z, which is y divided by this lambda of x. So the new in the z variable, u will vanish when z is equal to 1, right? So that may be a very simple way of fixing your free boundary. Then it becomes fixed. Okay, so we do that. It works well. However, there is a difficulty, because now the problem remembers that there is a free boundary behind, right? There was a free boundary. Mu is, yeah, you remember, like, yeah, you remember. Okay, maybe I should, I don't want to say that you remember, but it's more like my free boundary is lambda equal lambda g, so this is the unperturbed one, plus epsilon this e of x, right? And right. So now I make also the change of this kind of change of the S variable, that's the mu. The mu is the free boundary but in the S variable. Okay? So, so now the hope is that we get a problem which is positive parabolic here, forward parabolic here, backward parabolic here. Okay? The only thing is that the free boundary keeps appearing. So here I did something else. I wrote the equation in terms of the good unknown, omega g. Omega g is the good unknown after I got rid of these two terms, right? That was so basically close to the interface. This is the right equation. So this is the right equation, but only here in this neighborhood of the interface. Okay. I need to do something else away from the interface. I have to couple that with some other kind of analysis away from the interface. Okay. So it turns out that this term at the beginning we were afraid of it because it has an S derivative, but it turns out that we can really link it to some trace of the velocity. So it is linked to some trace of the velocity. So in a sense we can make another good unknown and put it inside, right? So I can still think about it as the S derivative of some other good unknown. So it's not really a big problem. So again, I mean, I'm always repeating the picture, the way you have to think about it, forward, backward, but there is also some information going like this. Okay. So I would like to explain two things in the proof now. Besides, in addition to this croco, I'm going to try to explain the other kind of transformation that we do, the von Miles type. But I'm going to explain also what we do at the interface. Okay, now at the interface, this is actually, I can go fast on this. This is actually another way of seeing this cancellation. This cancellation can be seen by another change of coordinate. I mean, you do this change of coordinate you call y, which is the u bar. The u bar is, you see now, at the interface, this is what I call w bar. W bar is the velocity. Here it vanishes at the interface. And I'm assuming that when I take the y derivative, it's bigger than 0. So it really moves from negative to positive, right? It's not degenerate. So, so it makes sense to introduce capital Y as W bar. So that's your new variable in this region. So that's my W bar. Then, if you make the change of coordinate, you take the stream function, you write it here, it turns out that you get this equation. Then I can fix this to 1. Then I end up with this equation. So this is really the equation that describes the dynamic here. So it's, and this actually omega is more or less the same as this good unknown. It's exactly the same, but so two different ways of rewriting it. But now the nice thing is that we have this equation, okay? So this reminds us something about Airy. It reminds us something about Airy if one takes Fourier in S. If I take Fourier in S, so I replace the ds by IXC, then that becomes like some Airy equation, but in the complex plane, right? Because there is an IXC. Right? If you just forget about this S, the ds, this is z omega minus dz square omega. This is really the airy ODE, right? If you put the IXC, okay, then you have to work in complex plane. I mean, I always, it's not always easy to remember where the airy decays and grows and so on, but okay, I mean, you can. So then, after you do this, so I'll try to explain it. I'll try to explain this part a little bit. After you do that, you get your omega, but you have to recover u. Even here in this interface, you have to recover u from omega. So there will always be, when you try to recover psi, let's say, from omega, you have some inversion formula, but then there are terms that are in a kernel that usually you have to control. I will not talk about that, but that's one difficulty usually. It's not very difficult, but it requires doing energy estimates and so on to control something that is not controlled by the omega on which we have an equation here. Okay, let me just go and explain what we do at the omega level. So here what we do, we have a data here. We have a data here, but we don't have a data here, right? I don't have a data here. So, but if I want the equation to be satisfied, I want, if I say, okay, I'm assuming the data gamma 1 of S, I'm assuming that omega takes the value omega gamma 1 of S. So one way of checking whether that is correct or not is to solve the problem here in the up, to solve the problem down, and then take the Neumann data that you get from up and down and try to make sure that they are equal, right? So this gives us some problem on deciding what is gamma 1, okay? So then you open a book about airy functions. I'm not going to try to explain like where it decays and grows because I think everyone is tired. But what happens is that you know the airy functions, you know normally how you can solve this knowing the right-hand side. There is some IXC because there is an IXC here. You have to solve up and down. I will not go through this. But basically what you get from the top, so knowing gamma 1, if I calculate gamma 2 from the top, so this is the Neumann data associated to this gamma 1, I see that there is something with IXC 1/3 coming times gamma 1. I do the same thing from the bottom. I see another IXC 1/3 times gamma 1, but with two different things coming from airy functions. Then you say that the two should be equal. And okay, the good thing is that this is a Wronskian, which is not 0, which is like a number. And then what you end up with is some equation C 1/3 applied to gamma 1 equal lower order terms, right? So this is something we say, we call it like some hidden ellipticity in the problem because these things are coming from the data. I'm a little bit cheating, they are coming from the data, but they may contain some lower order terms coming from gamma 1. Right, and that lower order term, that's related to that Schrödinger kind operator I was mentioning that that's the reason we have to avoid some values of L actually. So basically normally what you do, you just invert this, right? You just invert it. But as I said, the lower order terms may contain large term in terms of gamma 1. So when you put them here, if you want to invert now your fractional elliptic operator, you may need to avoid some eigenvalues. So again, this is really the picture that we have this operator on gamma 1 equals something you know. And that will fix for you what is gamma 1 here, and then you can solve up and solve down. Okay? Okay, so I'm going to skip this. I mean, this is one of the how you extend things in the inside. Let me not let me try to mention one thing I think which is the von Miles kind of transform. I guess people who are not familiar with Prandtl will see something maybe interesting here. So I explained this region, but then we have to understand what happens here and what happens here. We have to couple some energy estimates with, on the interface with energy estimate on the top and on the bottom. And then here, what we are going to do is von Miles. I mean, people who know Prandtl von Miles is very different from what I'm explaining here, but it is in the same, it is in the spirit. I'm doing this transformation, but staying in the same coordinate system. Usually when we talk about von Miles and Croco, you completely change your coordinate system, and clearly in a problem like this, that will not be practical, because I will be having some coordinate system here, some coordinates. You cannot, if I just change the variable, the functions, my unknowns, that make more sense. And that's what we do here. So, so I was saying that when this is positive, the good combination is that good unknown that I explained, which is the Croco type. Now, if you are now, if you are in a situation where U bar is positive or negative, if U bar is positive or negative, you have another thing you can do. Instead, I mean, how the thing that you want to think about this as one x derivative, right? You want to think about it as x derivative. So the idea is to, but then you have to work with the stream function, right? So I will be writing u equal psi y, v equal minus psi x. Okay, so so then psi y x plus v, we said minus psi x ui bar. And then let's say I'm not worried about that. So then here, what you can do, I can divide by this. Right? And introduce my new variable, which is this minus right? So then this is my new evolution. I write it on this quantity. Okay. This is something I used a lot in the work with Anne Lor. We use really things like this. And I mean, at that time, I didn't realize that this is the same as von Miles, because I mean, it seemed von Miles was another completely very different change of coordinate. But if one puts them together, it is really the same. But this is really the idea we use here and here. We use this kind of transformation. I mean, there are different ways of writing it. You can write it like this, but that's how we do our energy estimates. So then you have to do some energy estimate here, some energy estimate here. You have to couple them. And that's how it works. Yeah, maybe I'll... right, so now what about Navier-Stokes? Right, what about Navier-Stokes? So, I mean, we understand this region. We understand, like, before separation, we understand how Navier-Stokes is well approximated by Prandtl. Now we are working on trying to see how Navier-Stokes is approximated by Prandtl with reversed flow. That's a much harder question. But that what remains open is really to understand what happens here. And now in the physics literature, that usually goes with the name of triple deck theory. So there are some kind of asymptotics to try to describe what happens here. Okay, so maybe that's the end. So I'm going to finish differently than others. I want to thank Frank for handling many of my papers and ask him to send paper to the Tunisian Journal of Math. I'll be very happy to handle your paper, Frank, if you send us a good paper. And maybe this is also to ask everyone, like, if you have good papers, just send them to this journal. I mean, we need really good papers. We want to keep the level really very high, so we need excellent papers. Okay.
Okay, do you have some questions or comments?
Maybe,
Claude.
okay, a comment and question exactly on that. The last expression you worked, this picture. If you just care about existence, uniqueness of the solution, I think it's completely contained in the Bowen degree var in the old time, by energy estimate. On the other hand, if you want to have a qualitative description to see what's happened, you need really to do what you do, because it's more work than just saying there is a solution. You want to look at what is at the interface, and a theorem saying there is a solution in some subalect space will not give you all that. If you want to really look at there, but existence uniqueness is as old as this.
Yeah. So again, to go through what you said.
That you have to
right. So the Bowen degrees var. The Bowen degrees var. They are studying this. This equation. This is exactly the equation they are studying, but everywhere.
But then you have to work as an interior. Now I have a question, maybe naive. If you look at all this machinery for this type of problem, I have in mind two transforms. The one you mentioned, which is the Croco transform.
Yeah.
And then there is another one, which is called the Trichomy transform, which really, instead of looking at the position, at the velocity in terms of the position, you look at the position in terms of the velocity. That's what is done for trichomy, and it leads to equation with Sage type. It's well documented in the paper of Moravec in the old time, because we started from that for free mechanics. And there should be some relation there if we have to check this. Because it looks like, yeah.
The von Miles usually, classically, it is written as a change of coordinate in your new coordinate is psi, is the stream function. It's the stream function, because since u is positive, then you can go from y to psi. So now you think about your problem in the psi variable.
Yeah.
And then you can get rid of this term.
Yeah.
That's how classically the von Miles is done. But you can see here in here it would have been a headache to do it, like, because it becomes a completely different system. Also the the parabolic term then becomes it becomes it becomes quasilinear. So then you instead of this, you're still having a coefficient in front and so on.
Because you separate the elliptic from the hyperbolic by this trick.
Okay, so but we can talk. I get the reference.
Okay, so other questions? Yes.
Did you treat the pressure term or you got
Here the pressure is coming from the Euler, whatever you put for Euler.
So you do treat pressure?
Yeah.
It's a perturbation?
No, it's just given. It's just given.
It's a given.
Yeah, it's given.
You assume pressure is given.
No, it's not you assume. I mean, in Prandtl, the pressure is given from the Euler flow you have on top.
Okay.
So there's no pressure in Prandtl. I mean, it's given. It's.
Okay. It's really only depend on x?
Yeah, we can let it depend on x. Yeah.
Maybe one last question or comment? Charles.
Do you expect your solution to be stable or unstable if you look at the unsteady flow?
That's a very good question, actually. So, and yeah, I mean, like when I show this to a physicist, that's really the kind of question they will ask. And I mean, I had to look onto that. And actually, the answer is I mean, the answer is really like kind of pictures or video we can see. So the point, it depends on the Reynolds number. So what you expect in any kind of geometry, that if the Reynolds is very high, it's unstable because there are many other instabilities that will happen. Whereas in this kind of geometry, the Reynolds number where you expect instability to occur is like 10 to the 5. So then it means that if I go back now to the Navier-Stokes, and I take the steady case, the unsteady case, you expect to see this kind of picture if the Reynolds number is less than 10 to the 5, let's say. So still it's something you can see. And that's why we see, like there are pictures of separation and reversed flow. Those pictures, you see them if the Reynolds is not very high. If the Reynolds is high, immediately after separation, it becomes turbulent.
Okay. So I suggest to thank Nader again.
Thank you.